Today, automobiles and the fuels that power them are changing very rapidly. In order to meet federal regulations and consumer demands, auto manufacturers have responded with numerous technological advancements. First, there were changes like catalytic converters and EGR systems. More recently, there have been numerous modifications to the fuel, ignition, and air injection systems. Smaller engines, front-wheel drive, port fuel injectors, and computerization all add to the sophistication of today's automobile. The mechanic of the 60s and 70s is being replaced by the automobile technician. The petroleum industry is also experiencing rapid change, such as utilizing different crude oils, supply irregularities, and government regulations. Recently, lead phase down has required nearly the total elimination of lead as an octane enhancer. The struggle to achieve the octane previously supplied by lead has resulted in changes in the composition and characteristics of gasoline. In a moment, we will be conducting a class for auto technicians and automotive students who wish to obtain information about the changes occurring in today's gasolines. I'll be covering several topics today in this class that deal with fuel quality and how it relates to the automobile. The course will be based on this manual which you've been issued called Changes in Gasoline and the Automobile Service Technician. This manual was designed to fill a void in the area of information about fuel quality at the auto technician level. It's based on over 40 technical references and has been distributed to over 200,000 automotive technicians, automotive students, and service managers and instructors around the country. It serves as a course supplement in many vocational schools and training centers. It's important to realize when we're discussing fuel quality that the brief topics covered by the oil companies are merely commercials or advertisements. They do not cover the full realm of fuel quality. Advertisements such as high octane, high detergent, contains alcohol, contains no alcohol, all of these things are but one area of fuel quality. All of these items and many more determine the correct formulation and quality of a motor fuel. Gasoline is not a single substance, but a complex mixture of different ingredients. Each component has its own characteristics, such as octane and vaporization rate. The proportion of these components in gasoline are altered to meet fuel quality specifications. The recognized guideline for motor fuel quality control is the American Society of Testing and Materials, or ASTM. The gasoline specification is currently numbered D439. And it is based on the broad experience and cooperation of both auto manufacturers and the petroleum industry. D439 covers octane, fuel volatility, corrosion, gum, sulfur content, and fuel stability. While I'll spend time on each of these today, we will concentrate primarily on octane and fuel volatility because those are the areas that most often affect the auto technician and are most often involved in the diagnostic process. The first area I would like to discuss is octane. When a properly tuned engine is operated on the correct octane fuel, the air-fuel mixture will ignite from the spark plug. But if octane is insufficient, the mixture may ignite spontaneously instead of progressing from the spark. This is the source of engine ping or knock. Various circumstances can affect octane demand, such as air inlet temperature, deposits in the combustion chamber, for example. However, when the automaker specifies the octane requirement of a vehicle, they are primarily considering compression ratio. The higher the compression ratio, the greater the octane requirement. While most vehicles operate satisfactorily on the recommended octane-rated fuel, there are differences between different makes and even of engines of the same make and model. Using the correct octane-rated fuel does not necessarily guarantee knock-free operation, even when the vehicle is properly tuned. Generally, occasional engine knock will not harm an engine. However, prolonged knocking will result in power loss and could cause engine damage. In the petroleum industry, gasoline is assigned an anti-knock index, or AKI. This is the same number that's displayed on the gasoline dispenser at the local station and commonly referred to as pump octane. The octane rating is tested with a single-cylinder laboratory test engine. The AKI, or pump octane, is actually an average of two other octane numbers, the research octane number and the motor octane number. The refiner must formulate gasoline so that it has the correct proportions of each of these octanes. For instance, if research octane number is too low, the vehicle would have a tendency to ping under low speed, low acceleration circumstances. While if the motor octane number were too low, the car would experience pinging and engine knock during a high-speed pass, pulling a trailer, or climbing hills. There's also a minimum set on the motor octane number. For instance, in the Midwest, where the regular unleaded grade is 87 octane, the motor octane number would typically be 82. Therefore, your 87 octane unleaded regular would typically have a motor octane of 82, a research octane number of 92, and that would be the average of 87 that you see posted on the pump. One other point that I should mention is that altitude decreases octane demand. The higher the altitude, the lower the octane demand. For instance, the typical regular unleaded in the Midwest, as I mentioned, was 87, but in, say, Denver, Colorado, where the altitude's 5,000 feet, the same vehicles would require only an 85 octane. Are there any questions on octane ratings?
Is there really a significant difference between the premium grade and the regular grade?
Well, while regular unleaded is typically an 87 octane, the premium grades are usually 91 or 92 octane, and often as high as 93. In the case of a car with a high compression ratio or some turbocharged models, the extra octane is needed to ensure proper operation. Yes?
What about the new mid-grades? What are they?
The new mid-grade unleadeds are typically 89 octane, and they're designed for vehicles that may ping on an 87 octane unleaded but may not necessarily require a premium grade. In those instances, they provide the consumer with a way to stop engine ping without having to go to the expense of moving up to a premium grade unleaded. Yes?
Will higher octane grades provide better mileage?
Well, octane is merely a measure of a fuel's ability to resist engine knock. Once enough octane is provided to stop the car from pinging, there's generally little benefit in mileage or performance. Of course, with some of the newer computerized cars, they can adapt and take advantage of some of the increased octane. As an example, in a car equipped with a knock sensor, the automobile can advance spark to take advantage of the extra octane. And in those cases, there is a small improvement in mileage and performance.
Do older vehicles develop a need for a higher octane gasoline as the mileage increases?
That's a good question. As cars accumulate mileage, combustion chamber deposits can build up, and this results in a greater need for octane. This is where oxygenated fuels, such as ethanol, add an additional benefit. Because they enlean the fuel mixture, you get a better combustion and therefore lower combustion chamber deposits. Okay, the second area I'd like to discuss is fuel volatility. Fuel volatility is nothing more than the measure of a fuel's ability to vaporize. Since gasoline is metered in the liquid form through the carburetor or fuel injector where it's vaporized, the rate at which it vaporizes is very important. For instance, if the fuel evaporates or vaporizes too easily, it could result in hot drivability problems, vapor lock, and fuel foaming. On the other hand, if it does not evaporate or vaporize quickly enough, the problem could be a poor cold start or poor warm-up during cold weather. Gasoline volatility is also controlled by ASTM D439. There are certain volatility classes used to designate gasolines for geographic differences in seasonal conditions. For instance, a more volatile gasoline is manufactured in the winter months to provide easy cold starting. Less volatile gasolines are manufactured in the summer and warmer seasons to minimize vapor lock. These 5 classes are designated A through E, with A being the least volatile or hardest to vaporize, and E being the most volatile or easiest to vaporize. A and B gasolines would typically be considered summer grades, while D and E would be considered winter grades. There are 3 tests used to measure fuel volatility. The first is the distillation test. In this test, measurements are taken to determine the temperature to evaporate a certain portion of the fuel sample. For instance, measurements are taken to determine the amount to evaporate 10% of the sample. In a more volatile Class E gasoline, only 122 degrees Fahrenheit would be needed to evaporate 10%, while a less volatile Class A gasoline would require 158 degrees or 36 degrees more heat to evaporate the same amount. Similar measurements are taken at the 50% point, 90% point, and 100% point of the sample. Refiners also measure the volatility of a fuel by determining the amount of heat required to achieve a certain amount of vapor for a gasoline sample. In this test, the result is called the vapor-liquid ratio, or VL ratio. VL ratio is used to determine a fuel's tendency to vapor lock. The third test used to measure volatility is called the Reid vapor pressure test. In this test, a sample of gasoline is placed in a sealed flask and submerged in a 100-degree water bath. A less volatile Class A gasoline would exert only 9 pounds of pressure, while a more volatile Class E gasoline would typically exert 15 pounds of pressure from the same amount of heat. This particular test is beginning to be routinely performed in automotive shops. I'd like to go back to the distillation test for a moment. The numbers along the bottom are the portion of the gallon in percentages that would evaporate from the heat, which is listed along the left side in degrees Fahrenheit. As you can see, the first part of the gallon, or the front end, evaporates at lower temperatures. This provides a good cold start and warm-up. You will also note that the first half of the gallon affects hot drivability and vapor lock. If the line measuring the boiling points drops too radically in this area, the fuel would have a greater tendency to vapor lock. The mid-range, or middle portion of the gallon, affects warm-up and cool weather drivability, as well as short trip economy. Also, the last portion, or tail end of the gallon, should boil off by 437 degrees Fahrenheit. Fuels that do not boil off before this point could create problems such as incomplete combustion that would result in fuel running down the cylinder walls and diluting crankcase oil. There's a more detailed discussion of this in the manual. Before I cover the highlights of other fuel quality control parameters, are there any questions I could answer about fuel volatility?
You mentioned seasonal grades of gasoline. How does a refiner know when to switch from one grade to another?
When specifications are set for each geographic area, historic temperature data is considered. Based on this specification, D439 indicates which months a refiner would be required to change from one grade to the next. Of course, there's no way to predict abnormal seasons or early summer, for instance. This is one of the reasons that you have a tendency to see a greater incidence of vapor lock in the summer or spring months, because a refiner may be working off of a more volatile winter grade of gasoline, and in essence he's selling a gasoline that's too volatile for that particular day. Of course, this is entirely unintentional. Yes, another question?
Does anything besides temperature affect fuel volatility requirements?
That's a good question. One other important consideration is altitude. It takes less heat to boil a component at, say, 5,000 feet than it would at sea level. Therefore, certain considerations are made for the altitude in which the gasoline will be sold. For instance, in Colorado, a less volatile gasoline would be sold than, say, some other area at sea level that had the same temperature history. In addition to octane and volatility, there are other specifications that a refiner must control. A corrosion test is performed to measure the corrosion tendency of the fuel. Stability tests are conducted to determine deposit tendencies as well as storage life. Tests are also conducted for sulfur content, because excessive sulfur content not only creates engine deposits but also results in increased engine wear. Also, in the case of leaded grades, the level of lead is tested to ensure compliance with government regulations. Yes, a question?
You mentioned storage life. Can gasoline spoil?
In a manner of speaking, yes. Gasoline can become unstable in storage. It's typically manufactured to last 60 or 90 days. Beyond that, its stability starts to deteriorate and can result in gasoline gumming up. This is more likely to result in fuel filter plugging and induction system deposits. Additionally, when gasoline is stored over a long period of time, it could result in a winter grade being used in the summer or vice versa. Yes?
Is it difficult for the refiners to meet all the specifications at the same time?
In some cases, yes. Refiners may have to, in order to meet one specification, make alterations to the fuel. As an example, in order to achieve higher octane, some refiners may have to use more volatile components. Gasoline specifications are a little bit different than automobile specifications. For instance, when you're tuning up a car, you have an exact idle speed or timing to make that car perform as it should. But gasoline specifications have to encompass a variety of circumstances. When the refiner makes the gasoline, he doesn't know whether it's going to be used in a 4, 6, or 8-cylinder car, whether it's carbureted, fuel injected, casual, or high-performance driving. Therefore, the gasoline specifications are properly formulated so that all the numerous requirements can be met. Are there any other questions? If not, why don't we take a short break before we go on to the next topic. Now that we've covered some of the general guidelines for fuel quality control, I would like to get into some of the changes that are occurring in gasoline. Basically, the part where I'm at now in the manual is Chapter 2, which is the gasoline composition section. Hopefully this information will dispel some of the myths that exist about quality with today's motor fuels. Refiners are struggling to achieve octane ratings that were once achieved with lead. Over the last few years, the permitted level of lead usage has dropped from 2.5 grams to as low as 1/10 of a gram. 1 gram of lead is worth about 6 octane numbers to the refiner, so this has resulted in a change in the way refiners achieve octane ratings of gasoline. Trying to use different manufacturing processes to achieve these octane ratings has resulted in a different composition in today's gasolines. The first thing that refiners try to do to achieve more octane is to alter the manufacturing process to a more severe mode. This makes different high-octane components. And while this process does achieve octane, it results in changes in other areas of gasoline composition. These gasolines are typically higher in aromatics, such as benzene and toluene. Elastomer deterioration can result of high aromatic concentration. These gasolines are also higher in ingredients called olefins and diolefins. Olefins and diolefins contribute to fuel system deposits, for instance. In addition, the refining process results in more what are called lighter ends, products like butane, that while they are high octane, they have very low boiling temperatures and therefore increase fuel volatility. Prior to lead phase down, octane increases were achieved primarily with lead, and the actual composition of gasoline didn't change all that much. However, today, in order to maintain octane ratings just at the levels that are needed, gasoline volatility has been increasing dramatically. As this slide demonstrates, the average read vapor pressure of the unleaded regular summer grade has increased about 0.6 of a pound between 1979 and 1985. The second slide shows that the winter grade RVP has increased nearly a pound in slightly over the same period between 1979 and 1986. While these are national averages, they clearly indicate a trend of increasing volatility. Not all refiners alter their manufacturing process. Some do not have the necessary equipment, or it may be uneconomical to do so. In those cases, they turn to other areas or other refiners to purchase high-octane components, such as toluene, or they use alcohols and ethers. Alcohols and ethers are commonly referred to as oxygenates because they contain oxygen in their chemical structure. The U.S. Environmental Protection Agency, or EPA, controls the addition of oxygenates to gasoline, and they are in fact the most closely controlled ingredient in unleaded motor fuels. There are several oxygenates that have been approved by the EPA for the use in unleaded gasoline. However, of those approved, only 2 are widely used, and those are ethanol and methyl tertiary butyl ether, or MTBE. Information on other oxygenates are in the appendices in the back of this manual. However, we will not be covering those today. We will concentrate primarily on the most commonly used ones. One formulation that is not mentioned that I should probably cover is an oxygenate called petrocol. It has been used in the past, and it permitted high levels of methanol, up to 10%. High-level methanol blends have been concerned to the auto manufacturers because they can increase metal corrosion, elastomer deterioration, and they also significantly increase the volatility of gasoline by as much as 2 to 3 pounds. The reason I mention that is because while they're not being marketed today, there is some point in the future where, again, they could be used in the marketplace. Another concern of the automakers is the fact that on a methanol blend, methanol contains much more oxygen, and a 10% methanol blend would typically be 5% oxygen and would tend to lean the car beyond acceptable limits. It's important to distinguish between ethanol and methanol because there is some confusion in the consumer's mind. Ethanol does not increase volatility nearly as much as methanol, and it is much more compatible with today's fuel systems, elastomers, and metals. Okay, I'd like to continue now with covering some of the things with those commonly used oxygenates in today's market by giving you a little bit of background on each of them first. Ethanol has seen continued growth since the late 1970s. Originally, it was used as a product extender because of a shortness in gasoline supplies. Later, as gasoline became more plentiful, it began to be used as an octane enhancer, and the name gasohol, which had been used before, was sort of dropped in names reflecting, in favor of names reflecting the high octane value of ethanol, names like Super Unleaded Plus or Unleaded Plus. Ethanol continues to receive a good deal of support from a variety of groups, both federal and state governments, agricultural groups, environmental groups, and certain segments of the petroleum industry. Recently, areas of the nation have been considering using oxygenates like ethanol and MTBE to reduce carbon monoxide. These components result in lower tailpipe emissions of carbon monoxide and are therefore being considered as one option in reducing carbon monoxide. Some areas have actually already required that only oxygenated fuels be sold in certain months, and other areas are considering doing the same thing. Ethanol is already contained in about 8% of the gasoline used in the United States. In some states, it's as much as 30% of the marketplace. It has been used by many major companies as well as independent marketers. And I'd like to read to you just a list of some of the companies that use ethanol. Texaco, Amoco, Mobil, Super America, Chevron, Union, and Phillips. This is in addition to the many independents that use ethanol blends. Over 600 billion miles have been driven on ethanol blends to date, so it's not really a new product in the marketplace anymore. In the early years of use, ethanol was added to gasoline in a transport truck at the terminal located maybe away from the gasoline terminal. Today, the ethanol blending process is much more sophisticated. Ethanol is located inside the gasoline terminal and is metered into the gasoline to achieve an exact blend. Blends exceeding 10% ethanol are not permitted by law, nor are they likely to occur because ethanol costs more than gasoline, and therefore this makes high-level blends uneconomic. In addition to its octane enhancement and product extender capabilities, ethanol attracts water. It picks up moisture in the fuel system and acts as an excellent gas-line antifreeze. This same ability to absorb moisture, however, requires special procedures at storage terminals and retail outlets. For instance, in the early gasohol era, the sensitivity to water led to problems because service stations often have water in their underground storage tanks. Today, the petroleum industry is well aware of these considerations, and companies using ethanol have implemented procedures to eliminate moisture in the underground storage tanks. In the U.S., ethanol is produced primarily from corn. Ethanol should not be confused with methanol, which is much more sensitive to water, less compatible with fuel system parts, and increases volatility much more than ethanol. Ethanol increases octane by about 2.5 to 3 numbers and will increase fuel volatility slightly. MTBE is also a popular component to increase octane. MTBE has experienced exceptional growth in the past few years. It is permitted in unleaded gasoline to a level of 11% by volume. MTBE increases pump octane by about 2.5 numbers at the maximum permitted levels. However, it's most commonly used in the 7 to 8% range. MTBE is not as sensitive to water as the alcohols and usually will not increase fuel volatility. MTBE-enhanced gasolines are also being considered as a method of reducing carbon monoxide tailpipe emissions. MTBE is manufactured by a chemical reaction of methanol and isobutylene. The resulting product is an ether which does not retain any of the negative characteristics of the methanol used to manufacture it. I will cover the characteristics of ethanol and MTBE as we continue.
Will the volatility of gasoline continue to increase?
Probably not. In addition to affecting drivability, high volatility fuels result in higher evaporative emissions. Therefore, the Environmental Protection Agency is looking at regulating these gasolines and in fact would like to decrease the volatility of summer grades of gasoline.
Are there any further changes that will occur because of government regulations?
Well, that's always difficult to forecast, but one area that the EPA has been looking at is the aromatic content of gasoline, particularly benzene. Benzene is a known cancer-causing agent, therefore there's concern about limiting its use in gasoline. It is possible that if benzene content is controlled, because benzene is high octane, that the resulting products that would be used to replace the benzene would result in further compositional changes of gasoline. If there are no other questions, I'd like to continue with the subject of octane. Both ethanol and MTBE are widely used for their ability to increase octane. This slide compares the octane values of MTBE, ethanol, and toluene, a common refinery octane component, to the octane of regular unleaded gasoline. As you can see, the octane value of all three is significantly higher than gasoline. Therefore, they raise the octane of the gasoline to which they are added. As an example, if a refiner were trying to achieve an 87 octane unleaded and could only get to 85.5, he could add any of these components. As this slide demonstrates, all three products would achieve the 87 octane level and all would provide the minimum motor octane requirement of 82. The product the refiner decides to use depends on a variety of things, including economics, where the fuel will be sold, how it's to be transported, and which products may be manufactured by that refiner or one of its subsidiaries. In addition to being used at the refinery as an octane component, ethanol is often used at the terminal level, where it is added to gasoline which already meets specifications. This is because of the quality control measures used to ensure that ethanol does not come in contact with water. When ethanol is added to a finished gasoline, the resulting product is 2.5 to 3 numbers higher in octane. For instance, an 87 octane regular unleaded would typically increase to a minimum of 89.6 octane from the addition of 10% ethanol. Another area that is not well understood about gasoline is energy content. Some companies state that ethanol contains less energy and therefore could result in poor fuel economy. This is not a totally accurate statement. The energy content of gasoline is about 115,000 BTUs per gallon. However, this varies to some degree. For instance, since winter-grade gasolines are more volatile, they typically contain less energy. Ethanol contains about 76,000 BTUs, and when blended with gasoline, the resulting blend is about 3.4% less energy on a BTU basis. However, this does not necessarily translate into significantly lower fuel economy because the gasoline engine has never been able to totally utilize every BTU in a gallon of gasoline. In fact, tests have shown that in some cases the mileage or miles per gallon may actually improve on an ethanol blend. This is largely a function of air-fuel mixture. Vehicles that are operating rich tend to show mile per gallon improvements when operating on ethanol blends, while cars that are operating on the lean side tend to show mile per gallon losses. However, in either direction, the difference is very insignificant and usually only about 0.5 mile per gallon in either direction. Added to a finished gasoline, ethanol will increase the volatility slightly. Reid vapor pressure would typically increase between 0.3 and 0.7 of a pound. To put this into perspective, number one, the test used to measure the Reid vapor pressure is only accurate within 0.5 pound, but also refiners manufacturing gasoline can vary 0.5 pound from one batch to the next. Ethanol will also alter the distillation curve slightly. This illustration compares finished gasoline to that of a gasoline with 10% ethanol as illustrated by the dotted line. The curves are very similar with the exception that ethanol will have a slightly higher percent of product evaporated in the 150 to 200 degree range. If this portion of the gallon of gasoline contains significant amounts of other volatile compounds, the resulting blend may have a greater tendency to vapor lock. Most commercially available gasoline has a midpoint sufficiently high enough to allow the addition of ethanol and still meet the specification. Ethanol is often blamed for high fuel volatility and vapor lock when in fact other components in the gasoline should also be of concern. Ethanol and other oxygenates also increase the oxygen content of the fuel to which they are added. A properly formulated ethanol blend would contain 3.5% oxygen, while properly formulated MTBE blend would typically contain up to 2% oxygen. The 3.5% level is considered to be within the tolerance range of non-computerized vehicles and should not affect drivability unless the air-fuel mixture is already set lean. Computerized vehicles can adjust the AF ratio within certain parameters and will automatically enrich in the mixture when the vehicle is operating in the closed loop mode. One last area on ethanol blends is that of detergency. Surveys and fuel tests have shown that all major ethanol producers add a detergent package to their products so that the finished gasoline will keep port fuel injectors and carburetors clean. Gasoline detergents are not like detergents as we would think of them, but they are a special formulation of chemicals that are designed to eliminate or remove fuel system deposits. Additives such as detergents are another area of fuel quality that is taking on more and more importance. While detergent additives have received a lot of attention lately, there are actually many types of additives that are utilized to enhance fuel quality. In addition to detergents and deposit control additives used to eliminate or remove fuel system deposits, there are also anti-icers used to prevent fuel line freeze-up, and combustion enhancers to improve and modify engine combustion. An example of a combustion enhancer would be a lead scavenger used to prevent metallic deposits in combustion chambers of vehicles operating on leaded gasolines. Fluidizer oils are used with detergents to minimize intake valve deposits. Corrosion inhibitors are used to minimize fuel system corrosion and rust. In addition to these additives, refiners also utilize antioxidants and metal deactivators to reduce formation of gum and improve stability during storage. Refiners use these additives to enhance fuel quality and to meet fuel standards. Properly formulated additive packages can improve engine performance and drivability, lower deposits, provide better fuel emissions and economy, and increase engine life. There's probably no better example of the benefits of gasoline additives than the recent problems that were experienced with port fuel injection and the near elimination of that problem by using properly treated detergent gasolines. Are there any questions I can answer on gasoline components or additives that I've covered in this section?
From what you said, it doesn't seem like ethanol or ether blends are that much different from other gasolines. Why do some oil companies advertise that their gasolines do not contain alcohol?
Well, in most cases, those signs have a lot more to do with marketing than with fuel quality. In some areas, for instance, where methanol has been sold in the past, oil companies will put up signs that say contains no alcohol because they want to assure the consumer that their gasolines contain no methanol, because methanol may not be covered under auto warranties like ethanol is. And since the consumer has trouble distinguishing between ethanol and methanol, they will put up a sign using the generic term alcohol. Many of these same companies use ethanol in other areas of the country or have done so in the past. Yes?
If refiners really need more octane, does this mean we'll see the increase in ethanol and ethers?
Yes, the use of ethanol and MTBE are both likely to increase, and I'll continue to cover these products in more detail as we go through the class. But for now, why don't we go ahead and take a short break. Okay, now that we've covered some of the facts about using ethanol and MTBE as gasoline components, I'd like to continue by covering some of the specific topic areas of how these fuels relate to the automobile. One question that often comes up is whether or not ethanol and MTBE blends contribute to corrosion in the metal fuel parts in the fuel system. Most metal components in an automobile fuel system will rust or corrode in the presence of air, water, or acetic compounds. Gasoline distribution systems routinely contain water, and in addition to that, water can condense in the fuel system in the gasoline tank in the automobile. Pipelines which distribute gasoline routinely require that corrosion inhibitors be added to gasoline because they recognize that gasoline is corrosive, and therefore they want to protect the steel pipe, for instance. Because of this, corrosion inhibitors have been routinely added to gasoline for many years. MTBE is slightly soluble in water and therefore could increase the water-holding characteristics of gasoline by a very small amount. However, MTBE blends have not been shown to contribute to corrosion in the automobile fuel system. Alcohols are more soluble in water and therefore could contain slightly higher moisture than other gasolines. Because of this, several tests have been done to determine whether or not gasolines containing ethanol would contribute more to corrosion in the fuel system. Vehicles have been operated for extended periods on gasoline ethanol blends, and then they were disassembled, the fuel system parts cut open, examined, and photographed. These tests have generally concluded that ethanol does not contribute any more to fuel system corrosion than any other gasolines in everyday operation. One such test by Ashland Petroleum on 1983 model year Pontiacs concluded that materials compatibility of fuel system components of the late automobiles tested using ethanol extended unleaded fuel does not appear to be a problem. Fuel system corrosion was not evidenced in the vehicles tested using corrosion-inhibited ethanol extended gasolines. A similar test by Texaco was conducted on 4 1981 Reliance and 4 1983 Reliance and found that none of the gasohol fuel tanks showed any indication of premature failure. No functional differences were noted between any other fuel system parts, fuel filters, fuel pumps, fuel level sending units, and tank screens, which could be attributed to ethanol use. Ethanol producers have been working closely with both the petroleum industry and the auto manufacturing industry concerning fuel system corrosion. Ethanol producers have recognized that not all commercial gasolines are adequately protected for blending with ethanol. Therefore, they have began several years back routinely adding corrosion inhibitors to the ethanol. Additionally, the ethanol producers have been working through the ASTM process to set rigorous controls on moisture content of fuel ethanol as well as acidity levels. Therefore, you're not likely to encounter corrosion problems that are related to gasoline ethanol blends. Durability of elastomers with today's gasolines is another area that we should cover. Today's gasolines not only contain ethanol and MTBE, but they are also higher in aromatic content. Aromatics such as benzene and toluene have risen in gasoline to the point where they now comprise 25 to 40% of the gasoline content. One automaker has tested fuel samples and found aromatic content exceeding 50%. These higher aromatic gasolines have a greater tendency to cause plastic and rubber-like components in the fuel system to swell, crack, or otherwise deteriorate. The addition of alcohols and ethers can also contribute to elastomer swelling. Different elastomers react differently to these various compounds. This makes it difficult to identify the compound responsible for deterioration in a specific incidence. Identity is further complicated by the fact that the automakers are constantly changing various components in the fuel system to upgrade them so that they will accept a wider range of fuels. In the 1970s, the automakers began to be aware that there would be products in gasoline like ethanol and MTBE and higher aromatic content and began to routinely upgrade the fuel system. They began taking these steps nearly a decade ago. In general, from 1980 forward, you will find that the elastomeric components in the vehicle's fuel system are compatible with various formulations of motor fuels that exist today. In 1975 through 1980 model years, this was generally an upgrading period, and therefore these systems have also been upgraded, but not to the same extent as later models. Pre-1975 model cars may have fuel system components which are more sensitive to high aromatic content or ethanol or MTBE. While there's no documented evidence that indicates that these fuel system components in these older cars could be damaged, many of the fuel system parts were not thoroughly tested on all the formulations of gasoline that are out there in today's marketplace. Therefore, it's recommended that when replacing fuel system parts on older models that you specify that the replacement parts be of a formulation that's compatible with today's fuels. Those would typically be materials like nitrile rubber, and they're more compatible with today's fuel compositions. There is a table in the back of the manual in Appendix 3A that goes into more detail about elastomers and non-metal parts in the fuel system. One last topic in this area is fuel filter plugging. In the early years of ethanol use, there was a high incidence of fuel filter plugging. This was primarily because at the time there were a lot of cars that had operated on leaded gasoline, high mileage older vehicles. This is rarely a problem in today's newer vehicles which operate on unleaded fuels. One test by Purolator on various filters they manufacture found no premature failure and no premature filter plugging on ethanol blends. Nonetheless, you should be aware that this problem may occur in isolated cases where the vehicle's fuel system has had sufficient exposure to gasolines that leave deposits of lacquers and other compounds in the fuel tank and fuel lines. When this occurs, it is usually a one-time problem easily corrected by the changing of a fuel filter. Are there any questions on fuel system metals or elastomers? Yes.
I'm not sure that I understand the relationship between gasoline and elastomer deterioration. I've heard several technicians indicate that ethanol is the major problem.
This is an incorrect assumption on their part. Deterioration, if even fuel-related, can be the result of various gasoline components or combination of components. Ethanol often takes a bad rap in this area because it's the one ingredient in gasoline that's easily identified by a simple field test in the shop. Yes?
You said if deterioration was even fuel-related. What else could cause deterioration?
Well, first, elastomers were not meant to last forever. Age alone contributes to deterioration, and eventually some of these components will need to be replaced. Other examples of non-fuel related factors would be long-term storage or excessive temperature changes. Yes?
Will the automakers be able to continue upgrading these fuel system components?
Yes, several materials have already been identified and are being used in other countries. For instance, in Brazil, there are over 2 million cars that operate on pure ethanol, and the remainder of the fleet operates on a gasoline ethanol blend which contains 22% ethanol. In addition to this, General Motors and Ford are working with automobiles called flexible fuel vehicles, which will run on pure gasoline, pure ethanol, pure methanol, or any random mixture of the three. This is being done by the automakers in preparation for the day when crude oil would again be in short supply. The next topic I would like to cover is fuel system deposits. This is a very important topic because today's fuels have a greater tendency to result in fuel system deposits in some cases. At the same time, today's vehicles with their more precise fuel metering devices are more sensitive to fuel system deposits. Properly formulated gasoline additive packages are important in controlling this. Before I discuss some of the more current fuel systems, I would like to briefly mention carburetor deposits because it has in the past been an area of concern. In the past, it has been expressed that ethanol may contribute more to carburetor deposits. Tests have been done on this with contradictory results. However, the confusion has been largely eliminated by the ethanol producers adding detergents in their ethanol so that the resulting ethanol blend would provide detergency for both carburetors and fuel injectors. And although this was largely in response to gasoline components that plugged fuel injectors, it has addressed the potential for carburetor deposits. Again, I'll refer to a test, this one by Chevron Research Company. In this test, Chevron concluded that the 1980 inspection of 6 carburetors showed that gasohol had no different effect than gasoline on deposits when a carburetor detergent was present. They also showed that the addition of ethanol had no adverse effect on the additive's performance. The more current area of concern is the deposit fouling of fuel injectors or port fuel injectors. A great deal of confusion exists as to what really is responsible for plugging fuel injectors. Actually, there are several things that collectively contribute to this. Temperature of the injector environment, orifice tolerance and injector design, driving pattern, including hot soak frequency, fuel weepage, fuel composition, particularly the olefin-diolefin content of gasoline, and detergency, or the level of deposit control additives present in the gasoline. First, the injector itself functions in a hotter environment than a throttle body injector or carburetor. This contributes to the deposits becoming baked on the injector pintle and requiring high levels of detergents to address the problem. And of course, the injector itself has a small tolerance for deposits. It is a very precise instrument. The opening of the metering orifice is only about the size of a human hair, and so there is very little room for any error. This is thought to be a result of the amount of heat the injector is exposed to. Driving patterns can also contribute to deposit formations. PFI deposits do not occur when the engine is running, but rather after it's shut down. It's immediately after the shutdown, during the hot soak period, that the deposits form and become baked on from the increased engine heat. Therefore, vehicles which are driven on short trips followed by periods of frequent shutdown are more likely to foul injectors than vehicles that are, say, used on long trips or highway travel. Fuel weepage can also affect deposit tendency. The fuel system of a port fuel injected vehicle remains under pressure even when the vehicle is not operating. Therefore, some fuel can weep past the injector seat and become baked on during the hot soak cycle. These slides are of the Bosch design injector. Modification to this design, as well as new designs of injectors by other manufacturers, will be less sensitive to this deposit formation problem. There are also fuel-related issues with PFI fouling. Because today's gasolines undergo this more severe manufacturing process that I was talking about, they are typically higher in ingredients called olefins and diolefins. Olefins and diolefins result in a greater tendency for deposits throughout the fuel system, carburetors, intake manifolds, and of course fuel injectors. The high olefin content of gasoline, combined with the sensitivity of today's fuels metering systems, is the primary reason that increased detergent levels were needed. Insufficient detergent levels can also contribute to port fuel injector fouling. A sufficient level of properly formulated detergent or deposit control additive is needed to address these deposits. When one or more of these contributing factors result in PFI deposits, the result is a reduction in fuel flow and a distorted spray pattern. The automakers have indicated that as little as 10% loss of fuel flow on one injector can result in drivability problems. In addition to drivability problems, fouled PFIs also cause power loss, fuel economy loss, and increased exhaust emissions. Detergent levels are thought to be important enough that when the problem of fouled PFIs first began, General Motors sent a letter to more than 20 of the large petroleum companies and petroleum organizations stating that high olefin content and insufficient detergent levels were contributing to the problem. GM requested that detergent levels be increased. The Renewable Fuels Association, which is the trade association for the ethanol industry, also communicated with GM and was advised that by adding detergents to their ethanol, a large percentage of independent gasoline would be provided access to detergents it might not otherwise be able to obtain. Initially, GM put out a list of gasoline that contained detergents. In November of 1986, they put out Bulletin 87-6, which basically stated that all major brands, as well as many independent brands, now contain detergents. They included gasoline containing ethanol in this bulletin. GM stated that they would be doing away with their gasoline list. The bulletin said that customers should be advised to purchase gasoline from any marketer who advertises that their gasolines contain a sufficient level of detergent additives to prevent port fuel injector deposits. While the quick response of the petroleum and ethanol industries to add detergents has minimized deposit fouling of port fuel injectors, work continues in the area of valve and port deposits. Another concern about the greater deposit tendencies of today's gasoline is the possibility of increased intake valve deposits. Engineers have expressed concern that there is increasing evidence of greater deposits in the intake valve area. These deposits can also result in power loss, drivability problems, and increased exhaust emissions. A properly formulated detergent package should reduce deposit tendencies in both the PFI and intake valve areas. Many engineers believe this issue will take on increasing importance as vehicle manufacturers move to 4-cylinder 16-valve configurations, which will enable them to increase performance while still being able to retain fuel economy. I'd be glad to answer any questions you might have on fuel system deposits at this time. Yes?
You didn't mention whether ethanol fouls injectors. Why is it that so many experienced technicians would relate injector fouling to ethanol blends?
Okay, to thoroughly explain this, I should probably cover a little bit about the gasoline distribution system. Gasoline is somewhat interchangeable, and various companies put gasoline into the pipeline. And although it must meet specification, the gasoline that they get out at the other end is not necessarily the same product they put in. It's merely guaranteed to be similar. In fact, one company may actually load its trucks at another company's terminal. What makes the brand distinct is the addition of small amounts of proprietary additives. These proprietary additives usually contain the detergent. Pipelines do not want detergents in their system, so these additives are injected at the terminal much the same as ethanol. As an example, Company A may have companies loading gasoline at their terminal. In this situation, Company A would typically stock the proprietary additives for the various companies that utilize their terminal. When a company loads gasoline, the correct brand additive is injected into the truck with the gasoline. However, many regional brands and small independent companies did not have additive packages available when injector problems first occurred. These regional brands of gasoline contain no detergents or insufficient detergent levels. Many of these companies use ethanol, and so the technicians thought that the ethanol blends were creating the problem. Actually, this was due to insufficient detergent levels. This is why the ethanol industry first began adding detergents. This enabled the smaller companies who did not have access to detergents and detergent packages to offer a high-quality detergent gasoline.
You said gasoline is interchangeable. Are you saying all gasoline is the same?
Not exactly. Gasoline is required to meet specifications. For instance, the pipeline companies require that the gasoline that's shipped through their pipeline system meet specification. But gasoline can meet specification and still vary in composition. In addition to that, gasoline can be moved other than by pipeline. It could be moved by ship or barge or transport. Also, gasoline could be altered at the terminal level. Today, with all of the changes occurring in gasoline and things going on at the refinery level, there's probably a greater difference in the composition of gasolines than at any time in the past. If there are no other questions, why don't we take a short break? There are just a few other areas I would like to cover. As I mentioned earlier, today's gasolines tend to be more volatile. This trend of increasing fuel volatility is a major concern to the automakers for several reasons. One is that when a consumer has a drivability problem as a result of high fuel volatility, he often believes it to be a problem with the vehicle. This risks a dissatisfied consumer. Secondly, if the vehicle is under warranty, the consumer is usually going to bring it back to the dealership looking for an answer. This can result in cost to the manufacturer in diagnosing the problem. Most problems relating to excessive fuel volatility fall into the category of vapor lock or fuel foaming. In the case of vapor lock, the problem begins when a vehicle is shut down and the underhood temperature begins to rise. The fuel may begin to boil. When the still warm engine is started, it will start and function during drive-away when fuel demand is low, but when you accelerate, the fuel pump is windmilling full of vapor and does not deliver enough liquid fuel. The result, the engine dies lean or starved for fuel. Automakers have made and continue to make alterations to the fuel system to accommodate fuels of higher volatility. Changes in fuel pump pressure, speed, and capacity, and relocating the pump inside of the gas tank are a few examples. Some makes and models are more sensitive to fuel volatility-related problems than others. The more experienced technician rapidly becomes familiar with which models are more prone to vapor lock. There are also situations where individual vehicles may be more sensitive to vapor lock. These problems are not necessarily fuel-related. A thorough examination should include checking for such defects as a misrouted fuel line, missing insulation, or a marginally defective cooling system. Fuel foaming is a more recent problem. Some autos have fuel pumps with 60 to 80 times the pumping capacity needed for constant speed. In this situation, hot fuel may foam. That fuel bubbles out of the bull vent into the carburetor and causes the engine to operate rich. The consumer often confuses this with vapor lock. Of course, if the engine is dying rich, this can easily be identified by the puff of black smoke that occurs when the engine dies. Some manufacturers now have fuel foaming kits available for some of their models that are more prone to this problem. These problems, when a result of fuel volatility, are related to the high read vapor pressure, or RVP, of the fuel. A variety of components can raise fuel volatility, so the presence or absence of an ether or alcohol or any other component does not necessarily identify the problem. It is far more important to know the RVP of the fuel. Another area of discussion with today's gasolines is that of oxygen content. Both alcohols and ethers contain oxygen and therefore enlean the air-fuel mixture slightly. However, the increased oxygen content of these fuels are closely controlled, and this should not present a problem. One exception would be if the vehicle were already set too lean, in which case an oxygenated fuel would cause further enleanment. This is easily corrected by enriching the fuel mixture. Are there any questions on fuel volatility or oxygen content? Yes.
You mentioned enleanment. What about computerized systems? How do they react to enleanment?
Well, computerized systems can sense the uncombusted oxygen in the exhaust gases via the oxygen sensor, and then based on this they can enrich or enlean the fuel mixture within certain parameters to compensate for the oxygen content of the fuel. Yes?
What about the exhaust system and the catalytic converter? Will oxygen harm them?
Well, all unleaded fuels, including oxygenates, are controlled by the EPA, and one of their primary responsibilities is to be sure that no gasolines are sold that could damage anything that has to do with emissions from the automobile. We've covered several topics today about the effect gasoline can have on vehicle performance. Basically, these can be grouped into three broad categories: octane, fuel volatility, and deposit characteristics. It's not easy to identify all fuel-related problems. Octane tests require expensive equipment and therefore cannot be performed in the auto shop. The same applies to identifying components that increase the deposit characteristics of a fuel or the detergents that help to eliminate them. There are, however, a few tests that can be performed in the shop, and we're beginning to see more of these being performed as part of the diagnostic process. I'd like to discuss a few of these. The first area is identifying alcohol content. There are several kits on the market, or you can easily put together one on your own. All of these fuel tests for alcohol content are based on the principle of using water to separate the alcohol from the gasoline. Using that principle, I'd like to demonstrate a test to identify alcohol content of gasoline. This is a 100 milliliter cylinder, and it contains 100 milliliters of gasoline. You can take a gasoline sample such as this and use this device, which is a pipette, and insert 10 milliliters of water into the stoppered cylinder with the gasoline. Okay, then once you've put the 10 milliliters of water in it, you stopper the cylinder and shake it. And basically what you're looking for is when you started this test, you put in 100 milliliters of gasoline and 10 milliliters of water. And when you set this down to let it settle, basically, since gasoline does not retain water, the water will drop back out. And if there's no alcohol, you would get the 10 milliliter reading representing the water that you've put in. If there's alcohol in the gasoline, it will be pulled back out of the blend with the water. And so whatever reading you got above 10 milliliters would represent the alcohol content. As you can see, with this starting to settle out, we're getting a reading of 20, which indicates that the 10 milliliters of water has dropped back out of the gasoline and pulled out of it another 10 milliliters of alcohol. So in this particular case, we know that this gasoline was a 10% alcohol blend. There is one drawback to this test, and that is that it doesn't identify the type of alcohol. It could be ethanol, it could be methanol, we don't know. There are other kits available that are similar to this. For instance, some employ a small syringe that you can use. I prefer this particular size of cylinder and so forth because of the larger sample that you take, the more accurate you will be in identifying the alcohol content. As I mentioned, this doesn't tell us if this is an ethanol blend or a methanol blend, and that is a problem because at 10%, that's all right if it's an ethanol blend. That would be accepted by the automakers and covered under auto warranty. But if it's a methanol blend, it would be too high of a concentration of methanol. Also, with this test, it doesn't tell you if the octane of the gasoline was correct. It doesn't tell you if the fuel volatility was correct. It merely tells you that there's alcohol in the gasoline. Well, the gasoline could meet spec and still have alcohol in it. So I think that really it's of a limited value unless you're looking for, possibly a gasoline that has too much alcohol in it or something like that. A far more important test is the read vapor pressure or RVP test. The RVP test can be performed in the shop utilizing some relatively inexpensive test equipment. The test I have here is called a Miller gas check kit, and it has a variety of equipment in it. It contains equipment, a spiral steel cable inside of a flexible vinyl tube that you can use water paste to go down and test for water contamination in the customer's fuel tank. There's also some little pads that you can test for whether or not a car is being run on leaded versus unleaded fuel. And there's also a small cylinder similar to the one I used here to do the water alcohol separation test. In addition to that, you can do a read vapor pressure test with this kit. And what this device is something similar to what would be used in a laboratory, only it's designed for field use. A gasoline sample is put into this little flask and screwed into the bottom of this device. And then basically what you do is you take water and put in this thermal cup, and you use water, you put it in at about 105 because it'll cool off a few degrees before you can get the measurement. And you take the gasoline sample and set it down inside, and then you monitor the point, and at 100 degrees you will begin to see the vapor pressure measurement come up. And generally what you're going to be looking for instance, in the Midwest, a summer grade would be 11.5 pounds. If you get a reading above 11.5 in the summertime, you would know that the gasoline's too volatile for that area for that time of year. This demonstration is a bit oversimplified, and you should follow the exact instructions that are supplied with the kit. It also takes a few attempts to become familiar with the steps. For this to be of value, you do need to know what's acceptable as far as read vapor pressure in an area in a certain time of the year. And this information is readily available from various labs and other sources. I would say that, as an example, for instance, if a summer fuel in your area is specified to be 11.5 pounds, and you were to run this test and get a reading of 14 pounds of pressure, you would know a couple of things. First off, you would know immediately that the fuel could be contributing to vapor lock and hot drivability problems. Secondly, you could do the alcohol test. That would tell you whether or not there's alcohol in there. It would not necessarily tell you what was causing that high of a volatility reading, because ethanol, as I mentioned earlier in the class, only raises vapor pressure a half, maybe 7/10 of a pound. So when you get a reading of 14, you would immediately know that there's something else in the fuel causing the volatility to be too high. If a fuel is of excessively high RVP, a mechanical solution to the customer's problem may not be available. Are there any questions on fuel testing? Yes.
I think I understand the alcohol and RVP tests, but what about the tests we can't perform in the shop, such as octane?
Well, unfortunately, this is a problem. However, fuel-related problems are normally not isolated incidences. Usually, since many service stations in a given area are supplied from the same gasoline source, if there are, say, a fuel that would make it to the marketplace that was off-spec or of poor quality, it would normally result in numerous complaints across a wide variety of vehicles. In some states, they have control programs through the state and so forth that to control fuel quality, and I would suggest that the normal response would be that if you had fuel problems with a large number of variety of cars, that you would contact the state to advise them that there might be a problem with fuel in that area. Are there any other questions? Well, if not, I'd like to wrap up things with a few closing comments. I would encourage each of you to keep the manual that you were issued today. I hope that it'll be an important reference tool back in your shops. It may also assist you in explaining some of the types of fuel-related problems that can occur to the consumer. In addition to the items covered today, Chapter 4 contains the exact wording from the auto warranty owner's manuals for the various auto manufacturers. While it would be too lengthy to go into in detail here, I can tell you that all of the auto manufacturers cover the use of ethanol blends under their warranty coverage. All of them cover MTBE, and I believe there are a few that limit it to 10%. Some cover methanol blends, although not all do. Those that do cover methanol limit the concentration to the 3 to 5% range and require certain co-solvents be used with them. In general, then, the automakers cover the fuels that are available in today's marketplace. It's important that we stay abreast of changes in fuel and to be able to convey factual information in this area to our customers. Many still believe, for instance, that they cannot use 10% ethanol blends or that detergent levels of gasoline are unimportant. It is part of the responsibility of the auto technician to not only diagnose and repair the vehicle, but also to be sure the consumer is aware of facts which enable them to properly maintain their vehicle. Facts like the correct motor oil or the fuel for their vehicle. Today, perhaps more so than ever before, the type of fuel you select affects the vehicle. Not only performance, but maintenance frequency and emissions as well. That is why it's very important that the automobile technician stay current on the changes that are occurring in gasoline.
Over 40 references were used in the preparation of this program. If you would like information on the papers and the references used, or how to obtain additional copies of the video or the manuals, write Renewable Fuels Foundation, Suite C4, 201 Massachusetts Avenue Northeast, Washington, D.C. 20002. or call toll-free 1-800-542-FUEL.